Hi, welcome to this course. So we had a slight issue with the recording of this session with a cut in the beginning. So I'm gonna present what Hugo has done and then fill in the gaps for the first slide and then let you with the presentation of Hugo Guerin. So this course is about the production of radioactive ion beam with the in-flight method. So 3 weeks before, we had the presentation of Vincent Bosquet that is also available on the YouTube channel. That was about the ISOL method. And so here we are seeing a second method to make radioactive ion beams. So in this presentation, Hugo will present first the production of radioactive ion beams. Then he will present the in-flight method, and then he will focus on the LISE spectrometer. So starting with the production of radioactive beam, he will present the main production mechanism. The only one that was cut was the fusion evaporation. So basically, in fusion evaporation, you have the projectile, so the beam that will fuse with the target to make a compound, and then it will eject neutrons or charged particle by evaporation, creating exotic nuclei. And then the next is I will let you go for the following part.
After that, you can do multi-nucleon transfer. So your projectile and target will interact, and for instance, the target can transfer some nucleons to the projectile, and then you will also have a heavier nucleus and heavier product at the end of the reaction. You can also use fission to have radioactive ions. For instance, here it's a neutron-induced fission of the uranium-235, and then you have your two fission fragments and some neutrons. You can also do it by inverse kinematics, so by sending the EV ion. For instance, here I showed uranium 238 on aluminum 27. It will create a compound nucleus, which is here dubnium 265, which will fission into two fission fragments and neutrons. For higher energies, so for energies which are over much more 50 or 100 MeV per nucleon, you can have fragmentation. I will mainly focus on fragmentation because it's the usual mode we use on the LISE spectrometer. So you send the projectile, a heavy one, on the light target. For instance, in the LISE spectrometer, it's beryllium. And the projectile will break into many fragments. So you will have a large variety of fragments after the reaction. And you can then the last method is a spallation. It's quite the inverse. You have a heavy target and light projectile, and that is much more the target which will break into fragments. Here is quite a summary of this production mechanism I showed you. So it starts from, as you see, few MeV per nucleon to over 100 MeV per nucleon, like it could be a GeV per nucleon. And here you see the location of the product you have by these reactions. So you see you can have heavier products by these two reactions. And for the last ones, you have always lighter products. And as I said, I will mainly focus on fragmentation for the rest of this presentation. Then, so it was just to have radioactive ions, but you want a radioactive ion beam. So you need a stable ion source. so to have your stable ions, and the target, which is composed of a stable material. But the energy of the beam has to be higher than the Coulomb barrier, so you need an accelerator. And then, okay, I focus on the fragmentation, but you have not only one radioactive nucleus which is produced, so you will need purification. And this can be achieved by in-flight, the in-flight method, or the ISOL method. So Vincent told you about the ISOL method a few weeks ago. Why using the in-flight method? Okay, so in-flight uses the ion beam in a thin target. This is a fast technique. Fast technique could have short half-life nuclei. But you also have many products, so that's why you need a separation. And you have no chemistry as for the ISOL method, which means you have a huge playground, almost the Segre chart, which is not true, but you have really a large panel of nucleus available. And you have highly or fully stripped ions for fragmentation, so you don't need isobaric separation. Before starting, some reminder of the motion of an ion in a magnetic field. This leads to this so-called Lorentz force, which is Q, so the charge of the ion, via the speed, across the magnetic field. So this Lorentz force is perpendicular to the speed of the ion, which leads to a uniform circular motion with a radius we call rho, which is gamma mv over qb. And this leads us to the magnetic rigidity, which is in fact the only thing you have to know about the ion in the in-flight method. So this magnetic rigidity, we call it B rho, so magnetic field times the radius. And this B rho is P over Q, so gamma m V over Q. Another important thing for this in-flight method is the BED formula. BED formula is for energy loss in matter. So this formula. What you have to keep in mind is that the stopping power of a material, so the energy loss in a material, is somehow proportional to Z square. Z is the proton number of the ion. So now let's talk about the in-flight method. So you have the production of ions in the target. So it's here. Here you produce your radioactive ions or radioactive ion beam. Then you have to use quadruples, so in doublet or triplet, as a, no, I will say I do one, but it's not that, but in doublet or triplet to focus the will induce angular straggling. So you have to refocalize, sorry, the beam on the magnetic dipole. This magnetic dipole will do selection in magnetic rigidity. So you see here when the beam, so it's quite the envelope of the beam, enter the magnetic dipole, ions are deflected by their magnetic rigidity. So ions which are less important magnetic rigidity are much more deflected than ion with a high BRO. Then at the end of this magnetic dipole, you use also magnetic quadruples. So again, doublet or triplet to focalize uh, your beam. And then at the end of this first stage, you separate ions with their BRO, with a certain acceptance. Okay. But in fact, with these interactions, with this reaction in the target, a lot of ions have the good magnetic rigidity. So one need a second stage of purification. This second stage is done by energy loss. It is called so the energy loss selection. And why energy loss? So if you have two ions with mass and Z with the same magnetic rigidity after the target, so we saw this separation is impossible with 3s. Okay, with the first stage. So we need to distinguish their magnetic rigidities. That's why we had a wedge of material into the beam light. This wedge of material will induce like a loss, energy loss, which is proportional to z square. And for that, because of that, after this degrader, these two ions have really small chances to have the same magnetic rigidity again. That is explained here on this picture. So you have your first selection. Here are the slits. I did not mention about that, but if you do the selection by dipole, okay, you also need slits to select, in fact, the ions you want. So you make the first selection here with these slits. You can open or close them as you want. It depends on the purity or the intensity of the beam you want. This beam with the same range of BRO will enter the second stage with this second magnet. And because of this energy loss, ions have not the same BRO, in fact, is in this beam. So you can see ions which have less much energy with higher Z are much more deflected now. And they can pass this second stage, these second slits. So you can select, in fact, the ion with the good BRO 1 and BRO 2 here. But also you have to pay attention about the shape of your degrader. Because uniform degrader would lead to bad optical properties, okay? Will lead to losses, in fact. You will lose some ions. You need to adjust the shape of this degrader, and it has to be thicker for higher magnetic rigidity, which is in fact represented here. And here is like the shape of the degrader we have on LISE and on other spectrometer. It's like only a foil, but with a curved, which is curved, in fact. Okay, so you can do this selection with first and second step. I didn't mention about identification. I told you before, because we are at high energy, I guess I told you, but maybe not. The detection of the ions is easier than for low energy. So you have to pay attention of the counting rate. But with a silicon detector, in fact, you can have easily the energy loss of the ions, which will lead you to the Z of the ion. And with the time of flight of the ions, For instance, the times of light from the cyclotron to your detector, to your silicon detector. You have access to the speed, and which led you to the A over Q. And with these two informations, you are now able to have this plot, so energy loss in function of the time of flight, and each spot on this identification matrix is one isotope. If you have, like for instance, this straight line, a vertical straight line, as for A over Q, which is constant. These lines here, curved one, are for TZ, for the same TZ, isospin. And those lines, so for this line here, is for ions which are the same Z. So, okay, the same element. So with this identification matrix, you are able to know which ions you have in your beam. Just I make a comparison between in-flight and ISOL method, and then I will give you an example with the LISE spectrometer. For the in-flight method, I told you this is a fast technique with, in fact, bad optical quality. Bad optical quality meaning you have beams with high emittance. Since we have no chemical selectivity, we have almost all nuclei available and easy identification of the ions at high energy, because I told you I mainly focus on the fragmentation method. For the ISOL method, this is a slow technique, so which means short half-life nuclei are not available, but you have good optical quality of the beam, so small emittance. Also, because you use seek target in the ISOL technique, you can have a high intensity REB. But with this chemical selectivity, not all the nuclei are available. So there is always a balance, I would say, between in-flight and ISOL method. It will really depend on the nuclei you want to study. So I finish with the LISE spectrometer. So I will present you this spectrometer. First of all, a bit of history of this spectrometer. So just between 1978 and 1982, so this was the GANIL construction. First experiment at GANIL occurred in 1983, and the first experiment in the LISE spectrometer occurred in 1984. Here I show you the scheme, the plan of the LISE spectrometer in 1984. The LISE spectrometer was only in two rooms, D3 and D4, and we'll see it extended then. So in 1990, we had the first experiment in the LISE 3 beamline. The LISE 3 beamline is an extension of this spectrometer by adding a VIN filter, and now the spectrometer has a third room, which is the D6 room. Here is a picture of the VIN filter. I will talk to you about the VIN filter later on. In 2001 was the first experiment on the LISE 2K beamline. This LISE 2K beamline was aimed at having a limit on magnetic rigidity higher. Now, with this beamline, you can have a magnetic rigidity up to 4.3 Tesla meter. And for the LISE 3 spectrometer, it's I would say only, but not in fact, 3.2 Tesla meter. And also because of the conception of this beamline, the geometrical acceptance is also increased by a factor 3. And the last upgrade, which was made on the LISE spectrometer, is the add of the quadruple triplet in D6, which is called QD6, for better focalization on the experiment. So here you have a picture of this QD6. Now, let's talk about the description of this spectrometer. The beams enter here in the D3 room. Here you have the production target, which is rotating, which can be in fact rotating target for high intensity beams. Here you have the first stage with the first dipole. The degrader is here, and here, in fact, it's the second stage. So you have the LISE 2K, and here's the LISE 3 beamline. You can see the VIN filter here, and here I just show you some identification matrices. So you have first, after the first stage, you have all these ions in the beam. After this second stage remains only, I would say few, but some ions. And with, in fact, the use of the slits and VIN filter, you are able to have really few ions at the end of the beamline in D6. So a good purification. In fact, the rejection power of the LISE spectrometer is up to 10 to 12. And I would say it's a 3 stages selection because of the adding of this VIN filter. So you have first one, second one with the wedge, and third one with the VIN filter. The VIN filter, yes, I will explain you why and how it works. VIN filter is an electromagnetic filter. So you have both magnetic and electric field, which leads you to electromagnetic force, which is Q E plus V cross B. The electric and the magnetic field are perpendicular, okay, and they are also perpendicular to the speed of the ions, which leads you to this equation, and you see because of that. Oh, it's French. If the speed of your ion have the good value, like E over B, your ion will not be deflected by this electromagnetic force. That's why it can be used. If your ion have the good velocity, it will not be deflected. That's why it's called a velocity filter also. And I will finish just to talk you how we do the preparation of the beam for experiment on this spectrometer. First, we have to do the focalization of the beam on the target, so it's with the operators. So here is the beam profile on the target. Then, second thing we have to do is measuring the thickness of the target. To do that, we do a simulation on the LISE++ code, and we first send the beam through the magnet without putting the target, and we measure the BRO, the magnetic rigidity. Then we insert the target, we measure again the BRO, and by comparing that to simulations, we can access to the real target thickness. We do the same for the wedge, and then we can start to set the spectrometer, meaning the B01, so for the first stage, B02 for the second stage, and slits intensity, because experiment will need intensity segment, and focalization on the experiment at the end of the spectrometer. So here is a plot what we had in D4. So D4 is after the first two dipoles. So it was without wedge, without degrader, and then by adding the degrader, we can have this. You see, only this nuclei. So for this special experiment, we only wanted silicon 34, and that we achieved in the last room, so D6, by moving the slits also. That's quite all I wanted to say about the in-flight method and the LISE spectrometer. I thank you for your attention. I hope I was clear. I'm not sure about that, but if you have question, please.